To intercept a comet is to fly blindly into a cosmic sandstorm. As Halley's comet tore through the inner solar system, an intercepting probe would have to plunge into its coma at 68 kilometers per second, a relative velocity fast enough to cross the Atlantic Ocean in 11 minutes. Out of that violent hailstorm of ice and rock, a single spacecraft survived thousands of physical strikes and a catastrophic communications blackout to deliver humanity's first direct look at the solid core of a comet. The 1986 return of Halley offered a rare observational window. For the European Space Agency, it became the perfect target for their very first deep space mission. In July 1985, an Ariane 1 rocket launched the Giotto probe from Kourou, French Guiana, setting it on a 10-month intercept course with the ancient celestial body. Navigating the millions of kilometers of deep space was a solved problem in orbital mechanics, but surviving the comet's abrasive atmosphere required an entirely different engineering approach. At a combined approach speed of 245,000 kilometers per hour, the physics of a collision change. Even a dust particle weighing 1/10 of a gram carries the kinetic energy of a high explosive. Standard heavy armor would have been too heavy for the rocket to lift. Instead, engineers utilized a design proposed by astronomer Fred Whipple back in 1947, a dual-layer bumper. The front aluminum layer was 1 millimeter thick. When a high-velocity particle strikes, both instantly vaporize. The superheated gas expands across a 23-centimeter gap, washing against a 12-millimeter Kevlar sheet. This dual design defeats the particle by scattering its energy. To ensure this shield always faced the incoming threat, Giotto was spin-stabilized. Rotating at 15 revolutions per minute, the gyroscopic force kept the spacecraft perfectly rigid, pointing the bumper forward like a battering ram. This passive, two-stage barrier was the only line of defense for Giotto's fragile instrumentation. On March 13, 1986, Giotto crossed the solar wind bow shock, the boundary where supersonic solar particles crash against the comet's atmosphere and plunged into the coma. This false-color ultraviolet image shows the massive scale of the hydrogen cloud surrounding Halley. The volume of the evaporating water vapor stretched for millions of kilometers. Exactly 122 minutes before closest approach, Giotto's sensors recorded the first of what would become 12,000 distinct dust impacts against the forward shield. These sequential images come from the Halley multicolor camera. Because ground control couldn't steer the probe in real time, the onboard camera tracked the brightest object in its field of view, slowly resolving the solid nucleus out of the haze. As the visual data sharpened, the probe flew into a concentrated jet of ejected material. The rate of high-speed collisions reached its critical peak. Then, exactly 7.6 seconds before the point of closest approach, a particle weighing roughly 1 gram slammed into the spacecraft. The impact shifted Giotto's angular momentum vector by a full degree. The spacecraft began to wobble, and its despun high-gain antenna swung away from its alignment with Earth. Inside the European Space Operations Center in Darmstadt, the live telemetry monitors went dark. With the probe tearing past the nucleus at nearly 600 kilometers, the signal was lost. For the next 32 minutes, Giotto relied entirely on its automated systems. Onboard thrusters fired in calculated bursts, fighting the induced wobble and slowly dampening the spin until the antenna locked back onto Earth. Occasional bursts of data eventually stabilized into a continuous stream. Giotto's automated recovery secured the most detailed telemetry and photographic data ever extracted from a comet. This glowing image from Giotto's final approach changed our understanding of comets. Researchers had expected to find a bright, reflective, dirty snowball, a sphere of ice lightly coated in dust. The data instead revealed a highly irregular, potato-shaped body, measuring 15 kilometers long and roughly 8 kilometers wide. It was not bright ice. The surface had an albedo of just 0.04, meaning it reflected only 4% of incoming light, making it darker than coal. This topographical map highlights another discovery. The violent jets of dust and gas were not erupting from the entire body. The activity was restricted to just 10 to 15% of the sunlit side. Spectrometers detected a surface rich in heavy, complex carbon compounds. Halley was a dark, organic-rich dirt ball with ice embedded inside it, overturning the traditional model of cometary geology. After surviving Halley, Giotto went into hibernation. 4 years later, in 1990, it was reactivated, performing the first deep space Earth gravity assist, using planetary momentum to reach a new target. In July 1992, the damaged spacecraft successfully performed a second flyby, passing within 200 kilometers of Comet Grigg-Skellerup to analyze its distinct environment. Hitting 2 separate targets proved the European Space Agency could lead complex, long-term interplanetary exploration. Which of Giotto's discoveries changed your understanding of comets? Let us know in the comments, and subscribe to Cosmora HQ. By flying into a cosmic sandstorm, Giotto gave humanity its first true face-to-face encounter with the ancient building blocks of our solar system.